All right, so having said that, the big picture idea here was in chapter 1, we learned a lot of vocabulary. So I'm going to be using that vocabulary regularly to try to help you get used to it and warm up to it. And that one of the things we learned about in chapter 1 was that in order to study a population, we look at a sample. And in order to investigate a particular parameter, like how tall the population is, we look at a statistic, like how tall my sample was. And so what we're going to begin to do in chapter 2 is look at how we organize and learn from the data we collected from a sample, how we look at the statistic and start to do statistical analysis. And in chapter 2, we're focusing on exploring the data with tables and graphs. So there are 4 sections in chapter 2. And today we're going to introduce 2.2, one of the most common ways to provide statistical analysis or graphical representation for data is using a histogram. And what a histogram will be, and we'll look at the definition in a minute, but just briefly to connect it to 2.1, again, I introduced 2.1 in an earlier class, and a video will be posted on Canvas with that introduction. But in 2.1, we looked at a frequency distribution or frequency distribution table. This is extremely common to use in statistical data analysis or summaries. And a graphical representation of that is called a histogram. So a histogram is a graph, meaning it's kind of an image or a picture that's created that illustrates the details of a frequency distribution table. And so that's what we're going to study. And it's one of the most common statistical methods used for analyzing data results. So that's what the section is about. So let's go on to the key concept. And it says, while a frequency distribution is a useful tool for summarizing data and investigating the distribution of data, again, that was from 2.1, an even better tool is a histogram, which is a graph that is easier to interpret than a table of numbers. I totally agree. And it is, just to be specific, a graph of the frequency distribution. So it's a graphical version of the same thing, basically. So to explore this key concept, we begin with the definition of a histogram. A graph consisting of bars of equal width drawn adjacent to each other, meaning next to or side by side each other, unless there are gaps in the data. So you may have bars that are separated because there's no data in there. The horizontal scale, horizontal is up and down. Of course, I just said that exactly wrong. Horizontal scale is side to side. I'm dyslexic, I always do that. Horizontal is side to side, and the horizontal scale represents the classes of quantitative data values. So quantitative from chapter 1 is numerical data, quantitative with the root word being quantity. And then that means you'll have numerical data, and classes were defined in 2.1, but briefly, a class is a range of values that the data may fall into. And so you're going to have different ranges of values on the horizontal side to side axis. So for example, let's say you collected data of a bunch of ages of people. So then an example of classes might be all the people that were 0 to 10 years old, then 10 to 20 years old, then 20 to 30 years old. Maybe you would break each class into a 10-year range of values for age. Then you would put those along the horizontal axis, and then that would cover all the possible ranges, maybe up from 0 to 100 or whatever your data range might be. Then vertically, up and down, the vertical scale represents frequencies, meaning how many of the data values fell within the class range. So if I had a class range and the first one was 0 to 10, then maybe the height of the bar might go up to 7. And that would show me that 7 of the people that I got the data from were between 0 and 10 years old. And then maybe in the, we'll say older than 10, but less than 20-year range, all of a sudden it went up to 50 because 50 of the data values that I got were people that were between 10 and 20. And that's the idea of what this definition is trying to describe for this kind of graph. Now, of course, it'll be very easier to understand what they're talking about by looking at these as an example. But if we try to visualize it while looking at the definition, that's what they're talking about. So let's get to an example sooner rather than later, because it will illustrate all of these details they're talking about. Important uses of a histogram: visually displays the shape of the distribution of the data, meaning are more of the values around the middle or more of the values on the high end or on the low end of the range of values of the data. You can see that with the graph in a visual way, so that's very, very helpful. Shows the location of the center of the data. So if you look at your horizontal axis and the range of values are all covered there, then the center of the data will be sort of easier to see in that scale. Shows the spread of the data, like how much of the data is high versus low or in the middle, and helps us identify something called outliers. Now, remember, when they have all these emboldened words, that means they're introducing them, using them for the first time, but they don't necessarily think you have a clear description in your mind already of what that is, and they may even define them specifically later. Like, what the heck is an outlier? We're going to define that later. Okay? So again, I'm going through these things a little bit more quickly just because I think it's easier to understand what they're talking about when we're looking at an example, because this is a graphical thing, than to talk about it without seeing it. So I'm going to keep moving forward. And here's our first example. Now, they're already showing us with our first example, they're defining a particular kind of a frequency histogram called a relative frequency histogram. But even if we just look at the picture they have before we get to that, the picture they're actually showing is just sort of a standard histogram. So on the left, you see a frequency table, which was defined and illustrated in 2.1. And on the right, you're seeing the histogram of that frequency distribution table. So what I was saying earlier is that the histogram is the table, but just in graphical form. And I usually recommend, honestly, to students that if they're trying to think about a table, that they make the histogram, because then they get the values of the table, but they also get a visual impression at the same time. And it's very easy to do using technology. Okay, so having described that, let's look at what we have in front of us. So the things on the left are range values for the data. Like it says time in seconds, it says 75 to 124. And then to the right of that, the frequency says 11. So what that means is in the data set that they were looking at, and as we can see below the label on the graph, these were McDonald's lunch service time in seconds. They used this same example and this same table in 2.1, so that's why they're tossing it up here without explaining it very much, because they did explain it in the earlier section. But what that means is that of the 50 data values they collected, 11 of them were in the range of 75 to 124 seconds. 24 of them were in this second range, etc. And so if you look at the graph, it's showing you the exact same thing. You can see along the bottom horizontal axis that the range of values of 75 to 124 would be in this range of 74.5 to 124.5. And that the height of the bar in that range goes up on the vertical frequency to a height level of 11. And that's because there were 11 values in that range. There were 11 of the data values that were in this value range. And similarly, there were 24 in the second range. And so this bar goes all the way up to a height of 24 on the vertical axis. And you can see these numbers by looking at the heights of these bars. And even better, when you make a graph like this in StatCrunch, which we will do a couple of examples of today, if you hover over the bar in StatCrunch, it'll tell you what the numbers are as well, so that you don't have to try to judge them off of the graph. And so this is an example of a histogram displaying the data of a frequency distribution. So let's pause here with our first example in front of us and ask if there are any questions, comments, or discussions about what we're looking at.
I have a question.
Fire away.
What's the difference between actual frequencies and relative frequencies?
Great question. So the frequency is how many fell into a particular class. A relative frequency would tell you what percentage of the data fell in a particular class. Meaning, instead of just saying, like if I told you, yeah, there was 11 values between 75 to 124. Well, that's very accurate. You know exactly how many were in there, but you don't know just with that information whether that's a lot or a little. But if I told you that that was 22% of all the data that fell in that range, well, then you have more of a sense of how popular that range was compared to the others and how much that is relative to all of the data that was collected. Does that make sense? Are you satisfied with that answer?
Yeah, thank you.
Yeah, so another name that makes it a little bit more clear for relative frequency histogram would be a percentage frequency histogram. Relative is a proportion which can be often represented by a percentage. And you could calculate that by first seeing how many data values there were. Like if I add up all these frequencies, I can see they add up to 50. And then the way you could convert the 11 out of 50 into a percentage is to divide 11 by 50 as a decimal and move the decimal 2 places to the right. And then you should see that that's 22%. Great question, since we are looking at a label of a relative. Now, this is not a relative frequency histogram, but actually they're going to look the same, because if your height is frequency versus if your heights are percentage of the data, it actually ends up with the exact same shape. And that's one of the other benefits of a frequency histogram, is that you're getting the frequency as well as the relative frequency at the same time.
Wait, can you explain how to make it, how to find the percent of the frequency?
Absolutely. So the percent in this range would be how many out of the total were in that range. And so you make the fraction of dividing how many were in that range by the total of all the frequencies. So if I add all these up, I get a 50. And so that would make this 11 out of 50, or 11/50ths. And then to convert that to a percentage, you divide out, oops, I lost my share. You divide out that fraction, meaning 11 divided by 50, and you put that in decimal form. And then in decimal form, you move the decimal 2 places to the right to make it a percentage. So if I take 11 and divide it by 50, I'm going to get 0.22. And then if I take 0.22 and move the decimal over to the right 2 places, I get 22, and that means 22%.
Okay, cool. That makes sense.
That's satisfying?
Yeah.
Great questions. Any other questions before I move to the next slide? Six out of 17. Okay. Critical thinking, interpreting histograms. Explore the data by analyzing the histogram to see what can be learned about CVDOT, which they're now going to explain. The center of the data, the variation, the shape of the distribution, whether there are any outliers, and time. So what the heck are they talking about? Let's see if they help us think about this. So they're starting with the shape of the distribution by giving us common shapes that you can see. And the first one is super important. This is called a bell-shaped or normal distribution. Whether the data that we are looking at is a normal distribution or not is going to be very important for the rest of statistics. And so we are just getting a first look here, but I always do like to highlight the things that I know are very important to your future in the class when you first come across them, so that you scrutinize them a little bit more closely, you try to think about them, you ask more questions, things like that. And they actually gave a cursory introduction to the idea of a normal distribution in the previous section in 2.1. So a bell-shaped distribution curve looks basically kind of a bell, like it's high in the middle and tapers out to small on the ends, and it's somewhat symmetric, meaning the same on both sides of the middle. Now they took this bell shape and had this one right below it slid over to the left, and it has a longer tail on the right. And so that's called skewed to the right, when the data sort of stretches out more slowly on the right as it tapers off, whereas on the left it drops off more quickly. Then they say that's skewed to the right. It can be a little confusing because the bump moved to the left, but it's called skewed to the right. You'll want to get used to that. It will affect your ability to get homework answers correct in the future. Similarly, if the bump moves to the right and there's a longer tail on the left, that's called skewed to the left. And then on this upper right corner, the shape here where it's all just kind of level across the top, that's called a uniform distribution. Uniform meaning everything is kind of the same. And in this case, everything's the same because all of the different range of values have a very similar frequency. You don't have certain values in the range that are much more frequent than others. If they're all kind of similar, then we call that a uniform distribution. Questions, comments, discussions about these common distribution shapes? Lost my chat window. Let's see if I can get that.
Professor, so like these graphs, they never have gaps, right?
They can have gaps, and actually they look at that a little bit in 2.1. That's certainly perfectly possible, but it's not very common. And when it does happen, it usually means that in your data, you probably had two different groups all lumped together into one group. So for example, let me give you an example where you might expect to see a gap or at least maybe two different bumps. Let's say I was getting the heights of all the DVC students, and I had a very detailed histogram graph of that. Well, in general, heights of people are normally distributed. However, the average height of women has been shown many times through data to be lower than the average height of men. And so you might have one little peak around the average height of the men and another little peak around the average height of the women because their two high frequency levels around their averages both produced a bump and a higher level of occurrence when you lump them all together. Does that make sense?
Yes.
I don't think you'd actually create a gap because those bumps aren't very far apart and there's still plenty of people in the middle. But if you had more extreme example of that, like let's say I put a bunch of coins together and I measured how heavy they were, well, then I'd have one lump with the weight of all the nickels and I'd have another lump with the weight of all the pennies, and there wouldn't really be anything in between because those are very different weights and there's no coins that weigh the same amount as halfway between a penny and a nickel. But if I lumped all my coins together, there might be a gap between those lumps. Does that make sense?
Yes. Yeah. Thank you.
Great question. Other questions, comments, or discussions while we're on this slide? Okay, let's keep it moving. So now they're going to talk more about this normal distribution. As I was just saying, of those slides they showed us, that was one of the most important ones to think about. What is the gap called, Xavier asks. I just think they call it a gap. That's the only term I've seen used. I don't think you'll see some special statistic name for when there's a gap. And again, what we're talking about in a gap is where the graph seems to kind of flow, but then all of a sudden there's a hole there or a place where there doesn't seem to be much or much lower or drastically reduced frequency, but then it picks up later, then they'll call that a gap.
All right, got it.
Okay, so it says, because this histogram is roughly bell-shaped, we say that the data have a normal distribution. And so they're now saying, this is bold, this is what normal distribution looks like. Think about this picture, and they're showing kind of the overall smooth version of that shape that the rougher green bars kind of are emulating somewhat. And then the skewness, as I was discussing when the graphs were up there, is when it's like a bell shape, but it's kind of leaning one way or the other. A distribution of data is skewed if it's not symmetric and extends more to one side than the other. So for example, if the bell is a little bit to the left, then the tail that it creates on the right is probably longer, and that's why that would be skewed to the right. I think that shows up backward in the video. In any event, so they had that in the images. Like I said, much easier to understand these things when the images are there. So data skewed to the right or positively skewed have a longer right tail. And not too surprisingly, data skewed to the left or negative skewed have a longer left tail. And then finally, they're going to talk about assessing normality with normal quantile plots. So this is a graphical thing that you can do in StatCrunch. And again, I will illustrate that. It's something you do in StatCrunch. So there's a criteria for assessing normality because, like I said, whether data is normally distributed or not ends up being very important to statistical work. So that's why they're hammering on this point very quickly. A normal distribution, the pattern of points in the normal quantile plot is reasonably close to a straight line. So they're talking about making this thing called a normal quantile plot and then looking to see if the points that you get when you do that seem to be close to a straight line. We would need to see an example, so we'll look at that in a second. And if they are, then you might say that it's normally distributed. But if they're not, or if their closeness has some pattern of deviation, if it says here the points do not show a systematic pattern that is not a straight line, that would indicate that you may not have a normal distribution. But let's look at examples. This is 1 of 5, so let's move forward. Not a normal distribution. The population distribution is not normal if the normal quantile plot has either or both of these conditions. The points do not lie reasonably close to a line, or they show a systematic pattern that is not a straight line pattern. If both of those things don't happen, then we conclude it looks like it could be normal. But if either one of those occur, then we say it's probably not a normal distributed set of data. But let's see what they're talking about. So here's an example. So the points that they were talking about are these black spots here, and each one of those comes from a data value. So you will have a point for every data value in the set of data that you're looking at. Then on this graph, they've drawn the straight line that's the best fit to the data that's there. Of course, the data is not perfectly on a straight line. So this is the data, this is the line that would be as close as you could get to what line would be the same as the data points that you're looking at. And then by putting the best line you can think of in there, you can assess whether you think it's pretty close to a straight line or not. So I have a big question here about number 7, chapter 2. Okay, so I'm not going to try to go through all that right now, Randy, but how about this? When we finish here, I'm going to take us to homeworks and maybe we'll look at number 7 for you. So if you keep that in mind, it's just hard to read that and have everybody bring that into our process right now. But let me use that as an example, and then hopefully it'll be right on point and everyone can see the problem at the same time. Is that okay if I put you off to do that for a minute? Great. Okay, so having said that, so here they're showing us an example. It says these points are reasonably close to a straight line pattern and there's no other systematic pattern that is not a straight line. So they realize that this is a judgment they're describing, that you have to develop an ability to kind of assess the normality of based on the graph. And so they're trying to give you some examples and say, this is, we think, an example of what is reasonably normal. And then this would be an example of one that is not a normally distributed. The points do not lie reasonably close to a straight line. You can see that they're all lumped over here in the beginning, but then they spread all out to the right, and a line would not be lumped over here and then spread out to the right. And the best line that they could show to match this data here, actually really most of the points deviate very far from that line. So yeah, question.
Can't you also determine graph's normality by drawing a line of best fit and seeing if it's a straight line?
That is helpful, and that's what they've drawn for you in green. This is the line of best fit. So keep in mind, when you say line of best fit, you're already drawing a line. Mm-hmm. So you can't say, is the line of best fit a line? Well, it automatically is by definition. The question is whether the line of best fit is a good fit. Okay. And we will actually be drawing lines of best fit much later in the chapter specifically, but right now they're doing it for us and just asking us to judge, does the data fit the line well? And this particular line is the line for a normal quantile plot, and it's trying to assess normality. Does that make sense?
Yeah.
All right, so, but let's look here, assessing normality. Now, these stay pretty darn close to the line, but notice that it says this is not a normal distribution. Why? Because the way they deviate from the line shows a systematic pattern that is not a straight line pattern. You've got this wave going on here, which seems pretty clearly defining the way the data is working, and the wave is not aligned. So even though the wave's pretty close to a line, it's closer to the wave than to the line, and therefore we label this as not a normal distribution.
So the pattern has to be linear. Like it has to either go fully positive or fully negative. Like you can't have it start positive and go negative or start negative and go positive.
Not in a systematic way. So for example, this is a very good discussion to have to think about. Here, these points seem to deviate more from the line than the one we were just looking at. But the way they deviate seem to be still not very far and more random. They're not systematic. So that it's kind of equally likely that you're a little above or a little below the line on a particular point. Whereas here, there's a predictive pattern about how they deviate that suggests there's systematically something other than a line going on here. And that reflects back to then say that the population has something other than a normal distribution going on.
Okay.
Again, we're trying to develop a judgment call on this. All right, so that's the final slide. And so really the way to put these things to use is to apply them to problems to increase your judgment. Remember, the homework problems are infinitely repeatable. So if you're still a little confused and getting them wrong for a while, that is something that is not hard to overcome with a little bit of practice and possibly discussion or watching videos or looking at other examples. Any questions about anything on the slideshow before I leave it behind and take us to look at some of the specific problems where we might have to do them based on this discussion? So this idea of assessing normality, which looks a little bit more challenging that they finished with, I do want to point out is a much smaller portion of what's important in 2.2. The much more important thing is histograms. And notice that these things they're using here, where they're showing the shapes of the data, are all histograms. So these histograms are very important. You're going to need to make histograms for your project at the end of the semester. And histograms are one of the #1 graphs that's made in statistical analysis to help understand a data set. All right, so let's leave this behind and then let's get to the nitty gritty. And I'm going to keep recording because the examples that we go over are just as important in the slides, sometimes maybe even more so in this case. Let me switch over here. All right, and so I'm going to bump over and maybe I'll do one before I look at number 7, but Randy, I'm planning on number 7. It's in my list and we still have a good chunk of time, 25 minutes. So I do already have the sort of the homework, I think, set ready for us. Don't need that thing anymore. And let's start with number 5, and then we'll look at number 7 maybe as our follow-up. Okay, I have to go back to my math lab. You can do it. I guess it timed me out. There we go. Okay, so here we have one of the problems from our second homework set. You can see it's number 5 out of 49. And in this case, they are asking us, this is actually from 2.1, and I wanted to start with this because it's a 2.1 problem, but I think the easiest way to do it is use a histogram from 2.2. And so I'm pointing that out to you now so that hopefully if you're getting to these problems, you can recognize that the histogram is a better tool to do these kind of problems. Even though if you had just read what 2.1 and then gone here, you wouldn't have thought to use a histogram to do the problem. And also I want to use this as a way to illustrate StatCrunch as well. Okay, so just looking at the problem, it says the data represents a body mass index values for 20 females. Construct a frequency distribution, which is this table here, beginning with a lower class limit of 15 and use a class width of 6. Now they've already given us class ranges that begin with 15 and have a width of 6. And what they want us to do is produce the frequency of the data that would be within each of those classes. Now here's the data. It's just a big table of values. So actually, it's not too huge. There's only 20 values here. This is a 5 by 4 table. So Can someone suggest what we would do just looking at this right now if I wanted to just fill out these frequencies myself by looking at the data?
I would just use StatCrunch.
Well, look, you can use StatCrunch, and I'm going to show that in a second, which is great. But just to make sure people understand what we're talking about, how could you just do this yourself? Because it wouldn't be terrible to actually do this yourself.
You could just tally it between the ranges.
Absolutely. So what does the frequency mean? It means how many of the data values were between 15 and 20.9. And you could do that yourself by just looking through these 20 data values. And every time you come across one in this range, you sort of count off to yourself, there's one, there's two, and whatever you end up with is what the frequency is. And since there's only 20 of them, that would not be a big deal. Maybe certainly even easier than going off and figuring out how to use StatCrunch. However, very easily this data set, instead of having 20 values, oh yeah, it says right here, there's 20. There could be 200. And then very quickly that would become onerous, challenging, time consuming to try to go through and tally all of these for each class range, because they're not even arranged in order. If you notice here, they're just in random order, just whenever those numbers came up. And so that could be very much more pain in the butt. So what that means is this is a good example of when we want to learn how to manipulate and tally up or analyze data using technology. So StatCrunch is my suggestion for our go-to program because it's free and easiest to use. Now, when they give you a data set like this in a homework problem, there's also this little box up here. And if you click on it, it says click to copy the table. It gives you some options, the first of which is to just open up the data in StatCrunch. Now, if you really want to use Excel, that's perfectly fine. You can open it up directly in Excel. If you want to copy it to a clipboard so that you can transfer it to some other program, like maybe Google Sheets, you're welcome to do that too. But I would recommend, if you haven't for some reason already made a commitment to use something other than StatCrunch, that you use StatCrunch. It will be the easiest thing for us to do. And I've shot a bunch of videos in module 3 about how to do things in StatCrunch. So having said that, let's take a look. If I open in StatCrunch, so it has StatCrunch up here. It has the Pearson logo, but StatCrunch is actually a separate website, not My Math Lab or My Stat Lab, but it's been built into the My Stat Lab problems. But for example, after this class is done and you no longer have access to My Stat Lab, well, you can still go and use StatCrunch to do statistical analysis. Obviously, you'd have to pay. It's free with My Stat Lab, but it's really cheap. And it's very powerful and very easy to use. So it's something where if in the future you ended up doing more statistics or wanting to make presentations for a business or for some job in the future, StatCrunch might be a very good option for that. And it's very cheap. So having said that, what we can see is that these 20 data values have been dropped into this first column of what we call a spreadsheet, this big list of boxes. And so the first thing I'm going to show you that is a functionality of basically all spreadsheets is when you have a column of numbers, you can organize those or sort those in different ways. So for example, it might be easier for me to tally up the frequencies if these were in order from smallest to biggest, because then I could just count directly down the list until I got past this first class. And you can do that on any spreadsheet by going up to the arrow that will highlight when you go over the first column label. And if I click on it, it gives you choices. And for example, right here, it says sort table in ascending order. And if I click that, then it'll rearrange the data values from smallest to biggest. And then, for example, if I'm trying to see what are the values less than 21, I can see that the first 3 are less than 21. And I could go over here and put in a frequency of 3. And then I could tally up much more quickly these other values. So in this case, that's one of the ways that this tool could make it easier to look at the data and work with it. Now, the best way in this case is, instead of doing any of this yourself, would be to have it make a frequency table with these classes that is illustrated with a histogram. So let me look at the StatCrunch now and talk about doing more things in StatCrunch. There's no need for students to try to go and learn all about StatCrunch right out the gate. There's lots to learn about any new program. Instead, the best way to approach it is to slowly learn more and more about how to do things in the program as the homework problems demand. Meaning, as you're learning a new topic in the class and doing a new homework, you'll learn how to do new things in StatCrunch, and you just parse it out. And I've organized all the videos about using StatCrunch that I've posted in Canvas by which chapter that video makes sense, and you need to do that skill in StatCrunch based on our chapters and our homework problems. And during that entire semester, happily, you see all of these sort of labels up here across the top, all of these tabs. For the whole semester, we will only use the tabs Stat and Graph. There's a lot of things in each of these, but all the other tabs we don't really need to use for the course of the semester. And a histogram is a graph. So if I go under graph, you'll see histogram is right there. And so that's how I would ask StatCrunch to make a histogram for this data, is by going to graph and selecting histogram. Having done that, it'll tell me, all right, how do you want to make the histogram? Well, when you have data in StatCrunch on a spreadsheet, usually the data is organized by column. In our case, we only have one data set and it was dumped into one column. So when it says select column, we would select the only choice that's available. But if you have other data sets that have different things in different columns, you can say which column you want to be created into made into a histogram. Then the other thing is we want specifically our histogram to have each bar represent one of the classes as described here so that we can answer this frequency values correctly. The StatCrunch program uses a different word for classes. It calls them bins. And so bins in StatCrunch is the same as classes. So when they say that they want the classes to have a lower class limit of 15 and have a width of 6, then you would say that your bins are going to start with 15 and have a width of 6. And then I would tell it to compute and it'll draw the graph for me. So I'm going to pause here before I do that. Any questions about how I got to a histogram or what I entered to make the histogram correctly? I can't seem to see the chat. So yeah, the window does not want to come up. So please speak up if you have a question about that so far. All right, so let's see what we get. So this is now a histogram of this data set, and the classes across the horizontal axis have been created beginning at 15 with a width of 6, which matches what they said in the problem. And the height of each of these bars is the frequency value that we're looking for. So maybe we can see, I already tallied up, there were three data values in the first class, and you can see that this first bar goes up to a height of 3. However, even better than that, I don't need to read that graphically. If you hover your mouse over the bar, it will give you the data values. The frequency was 3, and this was for the range of values beginning with including 15 up to 21, but not including 21 because 21 is in the second class. Questions about that? All right, so I need to fill in the other frequencies. Now that the program has done the work for me, the first one is 3. So then I would have 9, 5, 2, and 1. So I go over here and I say, okay, there's 9 in there, 5 in there, 2 in there, and 1 in there. Questions about how I did this problem by opening the data in StatCrunch and making a histogram to see the class frequencies?
Under, I'm looking at my StatCrunch right now, and under overlay distribution, did you click anything?
I did not.
Okay.
There's often more options than you would like.
Yeah.
And so often in the videos, I'm trying to just show you the minimal amount that you need to enter. But, you know, the nice thing is that, you know, you can explore, play around and learn what the program will do if you don't feel so time pressurized that you're just trying to get them done as quickly as possible with as little exploration as possible. And it really will warm you up to the program to do so. The power of StatCrunch is you can do a lot with a very little amount of effort, and the flexibility of what you can do is nice to explore from time to time.
I wasn't able to actually get it to look exactly the same as that one.
Well, you probably don't have the same data that I do. Every student gets their own data set.
Oh, no. Under question 5, I think I have the same exact data as yours. That's on the screen.
Are these frequencies what you're getting?
No, actually it just showed up
You
like,
don't have the same data set.
no, I think I just inputted something wrong. I'll figure it out though.
Well, the data you don't put in there, and then it just shows you. So maybe you typed it over here wrong when you were copying it from the graph. But if you said the graph didn't look the same, it probably means you had a different frequency of data.
It was just like one bar of data, like a huge blue bar. I probably inputted something wrong in the setting.
Oh, that sounds like you didn't get a class. So let me show you some of your options here. And this is really what we want to do. Look at it together. I appreciate that you're looking at this at the same time on your computer. That's the perfect thing to do. So let's say you want to edit what you did. You can go to options and notice it says edit. And also for later, when you want to print graphs and make them for your project, you can also print them or download them and things like that. But if I go to edit, then it brings up that window again. So it's probably the bins, because if you just had one class, then the bins didn't work out correctly.
Yeah, that was it. And I accidentally clicked a group, which you didn't have one. So yeah, I got it.
Yeah, great. Other questions, comments, or discussions about how we did this problem using a histogram and StatCrunch before we move on and take a look at Randy's number 7? All right, and let me just also point out while we're here, I shot a video posted already about how to do histograms in on Canvas in our 3rd module. All right, so as any of the homeworks, you can jump around and do the ones you want. So let's say I skip over to number 7 here, see what we got. Does this look like the one you're talking about there, Randy?
Yeah, that's exactly the one. I mean, the first portion was I was able to do. It was the second portion with the wording that I got kind of confused on.
Okay, so it says a lower limit 125, class width of 0.2. All right, so let's do what I just did, because I think we can do this the same way as the one I just showed you, except in this case, we have to do a little more work because they have these things. It says type integers or decimals rounded to the nearest 10th as needed. So they're giving you a warning here about what they're looking for and how you put in the data. If I look at the data set, yeah, a little bit more here, right? So not a ton, but still, I'd really prefer right away not to be doing any of this by hand. I'm going to open this up in StatCrunch. So as I was mentioning before, it's possible that you would have a data set that has more than one column. And this way you have an ability to apply, trying to get these both on the screen at the same time. That's pretty close. Apply the histogram to the column of your choice. And in our case, the classes are about the volts and how many volt values are in each range, not the day. So the volts is where we want to do our histogram to come up with the values for this frequency table. So I would go to Graph, Histogram, select the volts. Now for the bins, we have a starting value of 125, and it looks like we're supposed to use a class width of 0.2. So is that what you got, or is anything I did need to be discussed or explained better?
I mean, I thought the values would be different in the frequency as far as the bars. Those look consistent.
True. Why did you think they would be different?
Just because I would assume that the frequencies would be just different across the board. I mean, if you were flipping a coin, that would probably be accurate. But
well, remember, we just looked at different shapes of distributions, right?
Yeah.
And this one had a name. Do anybody remember what the name of this kind of distribution was?
Yeah, it would be a normal one.
Nope. Good try. Don't feel bad.
Uniform?
Uniform.
Oh, yes.
Uniform distribution is when all of the classes had about, in this case, exactly the same frequency. So this is a standard type of distribution that may show up, and I think it's showing up here because they wanted to have you be able to answer the question, does the result appear to have a normal distribution, why or why not, by recognizing that this is not normal, that it's uniform. Is that okay?
Yeah, I understand that. Yeah.
And then you could get each of these frequencies by hovering over. Of course, they're all 5. So you just, oh, they're all 5. So you would type 5s down here and then answer the question. Does that make sense?
Yeah, that makes sense. I just got a different version of the question where it did appear to be a normal distribution.
That should be possible. As I said, each problem will get each student will get a different version of the problem. When the homeworks are generated for each student, it's the exact same kind of problem, but they will randomly change around certain numbers or the data set so that students have some variance in what they get. Does that make sense?
Yes.
And also, when doing a problem, you can do a similar version of the problem, whether you got it wrong or whether you got it right. So if you got it wrong, you're like, oh, okay. And then you look at the answer and then maybe you figure it out. And you say, let me try that again. And then when you get it right, you get the credit. But even if you get it right, you can still ask it to give you a similar problem so that you can practice a little more if you're not feeling comfortable about your ability to. 2, 3. Okay, so I'm just going to use this. So I have a data set and I'm going to click and open in StatCrunch. So if you are supposed to look at a normal quantile plot or examine one to determine the normality of the data, then that is also a graph. And what StatCrunch calls a normal quantile plot is a QQ plot. So if I go down to QQ plot, then again, it'll ask us to pick the column. And that's all I'm going to do, and then say, okay, give it to me. And there's a normal quantile plot, and they'll show you each of the data values. Normal, and notice even though it said QQ plot to make the graph, along here they call it a normal quantile. So it is a normal quantile plot, even though in the little label in the pull down menu it was labeled as QQ plot. And then you could see the QQ or normal quantile plot and try to decide if you think it's linear, if it falls along the line in a way to indicate a normal population or not. So I wanted to throw that in to help people see that they could quickly and easily with the data set produce a normal quantile plot if so desired, if one of the problems wants you to do that, and that's how to do it in StatCrunch.
What do they mean by QQ plot? Like, is there a specific?
It's just their abbreviation for normal quantile plot.
Oh, okay.
I don't know whether the other Q comes from a different word in a different language when they generated that. I don't know. But that's a normal quantile plot.